Hello everyone, um, welcome to this calculus video on averages. It's been a while since I last posted. I haven't gotten time to record recently, but now I'm back and I'll probably be uploading at least one video a week from now on, and they'll probably be shorter. So with that said, let's get on to averages. So let's say we've got some function h, and we want to figure out, like, maybe it goes like this, right? Over some x change. So let's call this, maybe we can call this distance delta x, right? It's kind of how much your x has changed over this random interval that we're doing. And so let's kind of, the analogy that people are often given is, like, if you imagine filling up this function with, like, water or something, so it looks like that. And then if you were to make this like water and then have it kind of level out like that, it's like you can imagine like water, or maybe it's like putty, and you're like squishing this this big area right here. You're squishing this big area right here into this rectangle. Or again, you can also imagine water, where you have like the wall here, so the water doesn't leak out all the way, and then you're just letting it fall. And how does it fall? It falls kind of like this, right? So why do we care about what this value is here for h? So this right here is, right, our average value. And well, why do we care? Well, the cumulative effect, right, or literally the area under this curve is the same, right? This area is the same as that area because we've just squished and stretched the same area, right? And so this is really like, if h was this value if h was h average for this whole entire interval, then you would still get the same cumulative effect. And so this is what we call an average. And so we can kind of extract this visual definition to a mathematical definition pretty easily, right? So if you know that, well, this right there is a rectangle, right? So we know that the area of that rectangle would just be average times delta x, and the area of this rectangle is equal to the area of the area under the curve in this interval, which is just going to be the integral from x0 over here to x1 over there of h of x dx. And at this point we can just solve for our average value, and this is the classic formula that you'll see for average value. You may see it like written slightly more explicitly, where we define delta x to be x1 minus x0. And the reason I'm writing using this delta notation is because it's just intuitively a lot easier to process what that means. It's just like, oh, it's kind of a distance between 2 points. So now if you were to apply the fundamental theorem of calculus to this definition, you get something very interesting, right? So if you have here, let's just take a look at this numerator, and we'll say as h, so this is right here just plain old fundamental theorem of calculus. I'll just abbreviate that as FTC. And of course, so this big H is basically an antiderivative of h, of the small h, and so that's what we've written here. And so at this point, right, you can say h average is, I'll write delta x from now on, but you just know that it's the same as the x1 at the top minus x0 at the bottom. Then you've got this is what we wrote originally, and then when we write it in our new fancy fundamental theorem of calculus notation, we get something like that. And I'm going to use this delta notation again, right? So delta x is like our end minus our start point, and I'm going to also define delta h, capital H, to be h of x1 minus h of x0. So that's really, this big H is the antiderivative. It's not graphed on here, so you can't quite visualize it. But if you were to write delta H like that, just put that down here, then it becomes delta capital H over delta X. And so all of this looks, it looks kind of messy, but really, once you write it kind of compactly, usually how I'll write it, it'll say H average. And I just leave out the bounds because we know that there's going to be bounds here, right? That's equal to delta capital H over delta X. And we know that these two are the same because of the fundamental theorem of calculus. And so this right here will get you through like pretty much every single like average value problem you'll ever find on the AP Calculus exam. And if you're clever enough, you can also apply this to rates of change. So suppose we wanted to find like what the average was of h prime, for example. It's like, oh no, can we do that? Well, yes, we can. If we just, for example, let's say we're trying to find like what the average of g prime is, right? So we'll go ahead and we'll plug in that over here, right? So it'll become, so let's say h g prime. So right now I'm just using this formula, right? So everywhere where there's an h, I'm going to replace it with g prime. And over here, that's an antiderivative of h, right? We define h, the big H, to be an antiderivative of the small h. Well, what's the antiderivative of g prime? Well, yeah, it's just g, right? Because when you do take the derivative of it, you will get g prime of x. So let's apply this here now. You get g prime average. This is the average of g prime. Integral g prime dx. So again, shouldn't be too surprising. And then this here, right? Well, before we had delta capital H because we just had to assign some function to be the antiderivative. But now we know what the antiderivative kind of is. I mean, we know it's g already, so we can just say delta g over delta x. And again, this delta g is just going to be g of x1 minus g of x0. You might not find this delta notation around absolutely everywhere, but I think it's a lot easier than, writing it out fully. So yeah, that was the conceptual understanding of averages. In the next video, we'll be applying this to solve a few problems, a few FRQ problems. I hope this was helpful, and I'll see you guys in the next one.